Welcome to this lecture of calculus. In this lecture we will study the total differential of a function and differentiability. We begin with the definition of the total differential of a function of two variables. So let f of x y, which is equal to suppose z, be a function of two variables. Then the total differential of f is defined as, this is denoted by dz, and defined to be equal to del f by del x dx plus del f by del y dy, where this del f by del x represents the partial derivative of f with respect to x, and del f by del y represents the partial derivative of f with respect to y. So this is how do we define the total differential of a function of two variables. Similarly, we can extend this definition to define the total differential of a function with more than two variables. For example, now suppose we have a function, suppose f of x, y, z, suppose this is equal to w, is a function of three variables. Then the total differential of f is defined as, this is now denoted by dw, because we are taking w as a function of three variables x, y, and z, and now define it like this. First term is del f by del x dx, then plus del f by del y dy plus del f by del z dz. So now we can compare these two definitions when we have a function of two variables, f of x, y equal to z, then total differential is dz is equal to derivative of f with respect to x dx plus partial derivative of f with respect to y dy. Now similarly, for a function of three variables w, we define the total differential as dw equal to partial derivative of f with respect to x into dx plus partial derivative of f with respect to y into dy plus partial derivative of f with respect to z into dz. Similarly, we can extend this definition to the function of more than three variables also, and define the total differential of that function accordingly. Now we take an example. We take up this function and evaluate the total differential of these two functions. First, let's consider the solution of the first one. Here we are given z is equal to tan inverse of x divided by y. So here we can see that z is a function of two variables. Therefore, the total differential is defined as, then according to our definition, we will have dz is equal to del f by del x dx plus del f by del y dy. So here our function f is equal to tan inverse of x by y. So now here our function f of x y, this is equal to tan inverse x by y. Now first we shall evaluate what is the partial derivative of this tan inverse x by y with respect to x, then its partial derivative with respect to y. So now del f by del x, this is del by del x of tan inverse of x by y. Now we know what is the derivative of tan inverse of x by y. This is equal to 1 divided by 1 plus x divided by y whole square. Then we have to multiply it with the partial derivative of x by y, which is equal to 1 divided by y. So therefore, the final answer becomes, this is y divided by x square plus y square. Similarly, we can evaluate the partial derivative of f with respect to y, which is equivalently del by del x of, this is del by del y of tan inverse of x by y. Now again the derivative of tan inverse is 1 divided by 1 plus x divided by y square multiplied by the partial derivative of x divided by y with respect to y. which is equal to minus x divided by y square. So finally this becomes minus x divided by x square plus y square. So these are the two partial derivatives of f with respect to x and with respect to y. Therefore finally hence dz, which is equal to del f by del x into dx, and we evaluate, substitute the value of del f by del x, so we get y divided by x square plus y square into dx minus x divided by x square plus y square dy. Now simplifying this gives, which is equal to 1 divided by x square plus y square into y dx minus x dy. So therefore this is the final answer for the total derivative of the first part with respect to x and y. Similarly, we can take up the second part. Now our second part is given u of x, y, z. This is equal to xz plus x divided by z power 1. Then according to definition, we have to evaluate the total derivative of u. This will now be equal to del u by del x dx plus del u by del y dy plus del u by del z dz, because u is a function of three variables x, y, and z. Now we will evaluate these three partial derivatives of u with respect to x, y, z one by one. So now del u by del x, which is the partial derivative of the given function, which is xz plus x divided by z power y, and we have to take the partial derivative with respect to x here. So this is del by del x of this function. When we are taking the partial derivative of this function with respect to x, we have to treat z as a constant and y as a constant. So therefore, taking the derivative of this xz plus x by z power y by y is a constant. First of all, we apply the rule for derivative of x power n, which is nx power n minus 1. So here the derivative will be y into xz plus x by z power y minus 1. So this is why we have applied the rule for the derivative of x power n, which is nx power n minus 1, but instead of n here we have y, and instead of x here we have xz plus x by z. Now this has to be multiplied with the derivative of xz plus x by z. The derivative of xz is z, and the derivative of x by z is 1 divided by z. So this is the del u by del x. Similarly, we can evaluate del u by del y. So now del u by del y. Now this is equal to del by del y of xz plus x divided by z whole power y. Now here y is a variable in this partial derivative and x and z are constants. Now here we have to apply the logarithm rule to find the derivative of this constant power y, which will be equal to the same constant xz plus x divided by z power y into log of xz plus x divided by z. So this will be the partial derivative of this u with respect to y. Now in order to make this derivative more clear, we shall mention one example here. We know that if we have a function, suppose y is equal to a power x, then y is a constant, then dy by dx is equal to a power x into log a. And we are using this kind of a derivative in order to evaluate the partial derivative of this function with respect to y. Now here, since we are taking partial derivative with respect to y, that means x is constant, z is constant, x by z is constant. So here we have constant power y. And exactly we are the same thing here, constant power x. Now when we are taking the derivative with respect to x, we get e power x log a. So here we will get the same function. It's a power y into log of a. So this is the rule that we are using to evaluate the derivative of u with respect to y. Now we evaluate the derivative of u with respect to z, which is equal to del by del z of xz plus x divided by z power y. Now here again y is a constant, so we apply the rule for like z power n or x power n, which is y xz plus x by z power y minus 1. Now multiply it with the derivative of xz plus x by z with respect to z. The derivative of xz is equal to x with respect to z, and derivative of 1 by z is minus 1 by z square. So this becomes minus x divided by z square. So these are the three partial derivatives of u with respect to x, y, and z. So hence the total derivative of u is, which we denote by du. Now this is equal to del u by del x, and our del u by del x is equal to y xz plus x by z power y minus 1 into z plus 1 by z multiplied with dx. Then plus del u by del y, which is equal to xz plus x by z whole power y into log of xz plus x by z multiplied with dy, then plus del u by del z into dz, and del u by del z is equal to y into xz plus x divided by z whole power y minus 1 into x minus x divided by z square into dz. So this is the total derivative of u in this case. Now we take one theorem that qualifies for being the sufficient condition for differentiability of a function in terms of evaluating the partial derivative of a function. And we shall take this theorem without a proof. So here we have a theorem that helps us in how do we understand whether a function of two variables is differentiable or not. That means whether a function of two variables has a total derivative or not. So this is sufficient condition for differentiability. This states that if a function, we shall state the result for a function of two variables only. A similar statement will hold for a function of n variables as well. So given a function z is equal to f of xy, suppose it has continuous first order partial derivatives at a point say p of xy, then f of xy is differentiable at p of xy. So we have a very simple and easy to understand condition as how do we understand whether a given function of two variables has a total derivative or not. We just have to check if the partial derivatives are continuous at that point. So once we can verify that the partial derivatives are continuous, we can conclude that the function is differentiable. Now let's take one example here as how we can see whether the partial derivatives are continuous. So let's take an example in this case. This is show that the function defined as like this: f of xy is equal to x square minus y square divided by x minus y when xy is not equal to 1 comma minus 1, and this is defined to be 0 when xy is equal to 1 comma minus 1. We have to check that this is continuous and differentiable at 1 comma minus 1. So how do we do it? We just have to evaluate. We will evaluate the partial derivatives of this function with respect to x and y, and verify that both the partial derivatives are continuous at 1 comma minus 1, and then the above theorem will conclude for us that the function is differentiable at 1 comma minus 1. So let's take a solution. The partial derivatives are given by the first partial derivative with respect to x, which we can denote by fx at 1 comma minus 1. We can see this is equal to limit h tends to 0 f of 1 plus h comma minus 1 minus f of 1 comma minus 1 whole divided by h. Now substituting the value for the function f of x, y, this becomes limit h tends to 0. Now first of all we write this 1 by h here, so this is 1 by h, and then evaluate the remaining function f of 1 plus h comma minus 1. So we have to replace x by 1 plus h every y, and replace y by minus 1 every y. So this becomes 1 plus h whole square minus minus 1 square whole divided by 1 plus h minus minus 1. Then minus f of 1 minus 1 is defined to be 0 according to the definition of the function. Now when we simplify this, this becomes limit h tends to 0, 1 divided by h. Now this becomes 1 plus 2h plus h square minus 1 whole divided by 2 plus h. So this is equal to limit h tends to 0, 1 divided by h. This is 2h plus h square whole divided by 2 plus h, which is now equal to limit h tends to 0, 2 plus h divided by 2 plus h. Therefore we can say this is equal to 1. Now we evaluate the partial derivative of f with respect to y. So now del f by del y at 1 comma minus 1, which we can also denote by fy at 1 comma minus 1. This will be similarly limit k tends to 0, f of 1 comma minus 1 plus k minus f of 1 comma minus 1 whole divided by k. Now we can see this is equal to limit k tends to 0, 1 divided by k. Now we will substitute the functional values here. We get 1 square minus minus 1 plus k square whole divided by 1 minus minus 1 plus k minus 0, because f of 1 minus 1 is defined to be equal to 0. Now simplifying this expression, we will get limit k tends to 0 to minus k divided by 2 minus k. Therefore, as k tends to 0, we again get 1. So hence the first order partial derivative exists. Hence the first order partial derivatives exist. Now we shall check whether these first order partial derivatives are continuous or not. So now we have, if we just evaluate like this, fx at x comma y, so we will evaluate the partial derivative at any point x comma y. This will be equal to, we will just take a derivative which will be equal to del by del x of f of xy, which is equal to del by del x of, the function is now x square minus y square whole divided by x minus y. Now we will use the quotient rule for differentiation here, and we will get like this: x minus y into derivative of the numerator, which is 2x, minus x square minus y square into derivative of denominator, which is equal to 1, whole divided by x minus y whole square. So this is equal to 2x square minus 2xy minus x square plus y square whole divided by x minus y whole square. So this is equal now 2x square minus x square. This becomes x square minus 2xy plus y square whole divided by x minus y whole square. So therefore this is equal to x minus y whole square in the numerator divided by x minus y whole square, which you can clearly see this is equal to 1 for all x not equal to y. So therefore in particular, hence fx at 1 comma minus 1, this is equal to 1. Similarly, fy at 1 comma minus 1, this will also be equal to 1. So therefore we have evaluated, now we have evaluated the limit of the derivatives of f with respect to x at 1 comma minus 1. So this was the limit of derivative of fx at 1 comma minus 1, which we have proved to be equal to 1, and the limit of derivative of fy at 1 comma minus 1, that is also equal to 1, and also the functional values of fx at 1 comma minus 1 and the functional value of fy at 1 comma minus 1, they are also equal to 1. So hence what we obtained, hence limit like this xy tends to 1 comma minus 1 fx of xy, this is equal to fx of 1 comma minus 1, and we have proved limit xy tends to 1 comma minus 1 for the function fy of xy. This is also equal to fy of 1 comma minus 1, and all these values are equal to 1. So that means the first order partial derivatives of this function is continuous. Therefore, the given function, which is x square minus y square by x minus y, then is not equal to 1 comma minus 1 and 0 elsewhere. This is a differentiable function.